I'm here to talk about King's conjecture. And I wanted to start with kind of a friendly introduction to resolutions. So I'm going to start with Hilbert's syzygy theorem. So just a second. Okay, so I'm going to start with a polynomial ring and a finitely generated module over this polynomial ring. So let's say it's generated by G1 through GT are some generators for this module. I wanted to start with T naught. Okay. So there's T naught generators. And that means that I just get a surjection from the free module onto M. I'll call it pi. And this map just takes a basis element, EI, to GI. And I can look at the kernel of this map, and that's the set of relations among the generators. Okay. So let's also give those names. H1. So there's going to be, let's say, T1 of those. And these are T1 independent relations. So independent over the base ring. Okay. So I keep going, right? So this gives me a surjection onto the kernel, which gives me this complex. And this thing, for example, is the relations among the relations. So there's T2. T2 independent relations among relations. And I could keep going, presumably forever. And what does Hilbert's syzygy theorem tell you? This terminates. And it terminates in n steps, where n was the number of variables, right? This was a polynomial ring in n variables. Terminates in exactly n steps or sooner. And the modern way to say this is that every module has a free resolution of length n. So we would draw that as we have M. So we have M. And then we have this free resolution. And it terminates at R to the Tn. Okay. And there's a version of this in algebraic geometry due to Grothendieck. So if I start with a coherent sheaf F on a smooth, importantly smooth variety of dimension n, then I have a resolution by vector bundles or locally free sheaves. And that looks like 0 to En to E0 to F. And so this is length N. And this guy here, these guys here are locally free. Okay, any questions? Sorry, it took me a while to check the chat. All right. So maybe on projective space, I can do a little better. Okay, so these are just abstract locally free sheaves, and we don't have very much control of them in general. But if I'm on a nice space like projective space, Then I actually have a locally free resolution by line bundles. So I can get the same statement. Every sheaf has a locally free resolution. So that looks like the same thing. But now each of these EI are isomorphic to some line bundles on Pn. Okay. And so what class of varieties would have such resolutions? Well, it was conjectured by Burke, Escher, and Smith, I think in about 2022 or something like that, uh, that any smooth torque variety has this property. Let's add the word projective. I feel like that's missing here. Maybe not. Their conjecture. But I'll put projective to be safe. Okay. So they said, let, oops. Let F be a coherent sheaf on a smooth projective torque variety. There exists a locally free resolution where each term is actually a sum of line bundles, not just an arbitrary vector bundle. Okay. So in fact, this was proven by Hanlon, Hicks, Lazarev. And another proof was given by myself and Sapranov, where we gave a topological formula for the Betti numbers in these resolutions. And this was extended to toric stacks by Hahn. I think just in the last month, this Hahn paper appeared. Maybe 2 months. So these results are from maybe 2024, 2025, and then this year. And so I want to ask the following question. Is there a categorical interpretation? And the conjecture of King was that yes, this is explained by derived categories. So if you're not familiar with derived categories, briefly. Okay.
Thanks.
Thank you. Hi, Pranav. So okay, so the idea of King is that this can, well, I mean, maybe the idea of King, but not chronologically, because that was maybe 20, 30 years ago, was to use derived categories. Okay. So briefly, derived categories, their objects are like these resolutions. And the idea is that uh, we want to replace sheaves on X by certain non-commutative rings and look at free resolutions there. Okay, so I'm going to try to make that a bit more precise. So if X is a smooth algebraic variety, I'm going to define a tilting when a coherent sheaf F is tilting. Okay. So that means that first, for any other coherent sheaf G, there exists some I such that there's a non-trivial extension class from F to G. So this condition is also saying that F generates this category, this derived category. But explicitly, it just means that every sheaf that F has an extension class to any other non-zero sheaf. Okay. And 2 is really the tilting condition that X IFF is 0 for I non-zero. Okay. Okay, so in other words, the derived endomorphisms of F are just the usual endomorphisms of F. So what does tilting theory tells you? Well, it tells you that you can model the derived category using this endomorphism algebra. So if F is tilting as above, you set A to be the endomorphism algebra of F, and then the derived category of X is equivalent to the derived category of modules over this A. This is some non-commutative ring, and I'll give you some examples in a moment. And importantly, this takes complexes whose components are summands of F to projective resolutions. Well, let's say projective complexes. Okay, so okay, and briefly, the functors here are you just take a coherent sheaf G to this complex R-HOM from F to G, and you take a module M to this complex. Maybe I should put derived tensor product. You take M to this complex of coherent sheaves. So the simplest example is X is an affine variety. F is the structure sheaf. So this is my tilting object, is the structure sheaf. So in this example, I take F and it goes to R-HOM from, sorry, G goes to R-HOM from F to G, which because I'm affine, this is the structure sheaf, and this is the structure sheaf. This is just the global sections of G. So this is the usual equivalence between sheaves on an affine variety and modules. And the module is just similarly going to go to its the sheaf, Hartshorne's tittle sheaf of that module. Okay. Any questions? Okay, so maybe an example of balancing uh, is if I took Pn, I have this tilting sheaf, which is just the sum of n plus 1 line bundles. Okay, just take all twists from 0 to n of the structure sheaf, and that turns out to be tilting. And so the derived category of Pn is also modeled by the derived category of some non-commutative algebra. What is that? Well, A was the endomorphisms of this sheaf, which we know how to compute. We can use the projective coordinate ring. And what is this? Well, if I took this as a free module of rank n plus 1 and this as a free module of rank n plus 1, I'm going to get n plus 1 by n plus 1 matrices, right? But I only take graded pieces when I compute these HOMs between each other. So I take the degree 0 piece of this. Maybe I should put a little 0 here. Okay. Um, so I get n by n plus 1 by n plus 1 matrices, and then the ijth entry is homogeneous of degree j minus I. And people often draw this picture called a quiver of this algebra. So, for example, for P2, you would draw this picture. So this dot represents O, and then I have another dot which represents O of 1, another dot which represents O of 2. And then I want to draw endomorphisms of these three objects, so I know I have three maps, or linear combinations of three maps from O to O of 1, I have X, Y, and Z. Similarly, from O of 1 to O of 2, I have X, Y, and Z. If I wanted to consider maps from O to O of 2, I could get them from concatenating. So I get X times X is X squared is a map here, or X times Y is a map here, etc. And then, of course, these have to obey the commutativity relations. So I take the algebra of paths. It's called KQ, is the algebra of paths in this quiver. So I can take any kind of directed path, which makes sense. And I have to mod out by the commutativity relations. So that's this ideal generated by the commutators. So x times this y is this y times this x, etc. Okay, so this is some non-representation of this non-commutative algebra. That's just to give you a sense of the kind of algebras you work over here. Okay, and now what's the consequence? So if I take any sheaf G on Pn, it has a resolution. And I should terminate this. Let me actually say more here. So I'm going to add in. By sums of line bundles. Okay. And this length is actually, this has length n. And better, these line bundles fall in a finite set up to a twist by some big ample line bundle. So why is this a consequence? Well, the idea was we had the derived category of X, derived category of Pn, and if I took a sheaf G in the derived category of X, Well, I sent it to R hom F to G. So I could twist it, and I'll just get R hom F to G twisted by N. And Sayre's criterion tells us that there's no higher X if I choose N sufficiently ample. Okay, so I just get hom. So the point is that this thing, this is, so if I just get hom, this is an A module. Okay. And that means I can take a projective resolution, let's call it P. This is a projective resolution. Okay. And now I just send P back via my equivalence. And well, this becomes underived because P is free. And so I get a complex. This looks like this is a complex of locally free sheaves. Or actually, let me say a complex of sheaves whose components are summands of F. Okay? And then if I wanted to get my original G, I just twist back. So if I take this complex and twist back by minus n, I get a locally free resolution of G. Okay, any questions? Okay, so let's do quickly example of king. So King said, let's take the Hertzsprung surface FR. Okay. So that's the projectivization of O plus O of n on P1. So we have this projection map pi to P1, and I'll let D be the divisor for 0, 1 on this in this projectivization of this bundle. So I get King showed that this is a tilting bundle. So you just have to check some X conditions for this. So I'm going to let F, so this is just some explicit calculation to check that F is tilting. And I suppose you have to check it generates as well. So the bundle is, you take O of 1, and then O of 1 tensor D, and O of D. Okay, and this is tilting. And then the derived category of X is the derived category of the endomorphism algebra. Again, there's some kind of picture. I'll just say quickly, we'll gloss over this a little bit. There's some kind of picture like this. In this case. This is some kind of picture of the endomorphism algebra. Doesn't really matter, okay? And so a consequence is that any sheaf on a Hertzsprung surface has a resolution with terms O of 1, pi upper star O of 1, twisted by O of D, up to an ample twist. And so the question of King, which became known as King's conjecture, is does this hold for all smooth projective toric varieties? So Hertzsprung surface is an example of a toric variety. Maybe we can do this for all toric varieties. So the first answer to this question was by Hill-Perling, and the conjecture was famously false. So Hill and Perling showed this fails for sufficiently bad non-Fano surfaces. Okay. And so maybe people said, oh, well, maybe Fano is the issue. So, for example, Borisov and Waj showed that it was true for up to Picard rank 2 for Fano toric varieties, but it failed in Picard rank 3. So, in fact, Efimov showed the modified King's conjecture for Fanos was false. So this fails for high dimensional Fano toric varieties. The examples weren't very explicit. Michalik also showed no for the easiest case of examples. So he showed it fails. For you take the blow up in 2 points of Pn for large N. Okay, so that was the easiest set of examples. So maybe the takeaway here, is that King's conjecture is false. And then the next thing I want to tell you is to ignore this takeaway. So we had a large AIM meeting with people studying these resolutions, and we said, can this still come from King's conjecture? And the answer is yes, after some modification. So what do I mean? So it turns out that the derived category of X, it always embeds into what we call the Cox category of X. And this thing has a tilting object. And the Cox category, I'll describe it a bit more in a second. So this is where d Cox of X, the Cox category, of X. So this thing is, I'm going to describe it in a second, but it's roughly the category generated by all toric birational models of X. And I'll be slightly more specific. But I want to say the consequence, which were the earlier mentioned theorems, is that any smooth projective toric variety admits a resolution by line bundles. So this recovers the Hanlon-Hicks Lazarus resolution and the work of myself and Sapranov. Okay, so let me describe this cat. So are there any questions? So I told you maybe this theorem is false, and but now we have some correction where it's true. Are there questions about that before I go slightly more technical? Okay. So let me give you a slightly better description, but probably not entirely rigorous or detailed description of decox. So the setup is really X sigma is a simplicial projective torque variety. If you like, you can work with projective over an affine. Okay, and there are finitely many simplicial projective torque varieties. So this is just torque geometry tells you there are finitely many simplicial projective torque varieties. X sigma 1. Actually, maybe this is entirely obvious through X sigma t. So these rays are a finite set. And then there's a finitely many ways to basically triangulate these rays or a subset of these rays such that it remains projective. Okay, so this is what I meant by these things, or is what I was calling the toric birational models. There's other, I mean, you might complain that all basically torque varieties of the same dimension are birational, but this is what I mean. Specifically, when I give you a fan, I only want to consider this finite set. Okay, so I can choose a common simplicial refinement of all these fans. This gives me a new torque variety, x tittle, and it has the refinement maps give me maps down. So this is some kind of rational map from x tittle to this guy. And I'm going to say this is again, I'll give you the caveat in a second. But morally, this Cox category is defined as this is a subcategory of the derived category of X tittle. Okay. And it's the smallest triangulated subcategory. Oops. So let me actually rewrite it. So this is the smallest, excuse me, smallest, sorry, triangulated subcategory of this refinement containing, oops, these pullbacks. I don't know what happened to this I. These pullbacks. For any I. So each of these guys is fully faithfully embedded. So so it's basically the category generated by all of these derived categories. And we imagine it sitting inside this refinement. You could ask me, well, you could take other refinements, etc. There is a categorical construction of this thing that's independent, that doesn't choose a refinement, but this is the simplest way to describe it. So this thing's independent of the, it's actually also just easy to prove this is independent of the refinement up to equivalence. Okay. And then why did I put roughly here? Well, it's because we really need everything to be smooth. So when you talk about simplicial torque varieties, they're kind of secretly smooth, but they're singular. They're singular if you considered them just as varieties. So every simplicial torque variety really has a stack associated to it. A nice smooth Deligne-Mumford stack associated to it. And actually take all these symbols to mean derived categories of stacks is the truth here. And that's unavoidable because if I go back up here and look at these guys, all of these birational models appear, and some of them will not be smooth toric varieties. You have to consider the smooth stacks associated to them. So I think I'm going to have time to get to an example at the very end, which demonstrates this. Even the Hertzebruch surface, this happens. Okay. So let me quickly give you a description of the tilting bundle. So how is the tilting bundle described? Well, I'm going to kind of cheat and just tell you there's something called the toric-Frobenius morphism. And I'll describe it if you know some toric geometry. So if I take a toric variety, I can look at the map on the lattice of one parameter subgroups of this toric variety. So this toric variety has maybe C star to the n in here, and this is isomorphic to n tensor over z C star. And this is the lattice of one parameter subgroups. Not so important, but it tells you that just scaling this lattice actually induces a map of toric varieties called the toric-Frobenius morphism. So all you really need to know is that there's something called the toric-Frobenius morphism on any toric variety. Okay. And there's a theorem of Thomson, I think from the 90s maybe, that says, maybe late 80s. So it says that if you look at the push forward of the structure sheaf under the toric-Frobenius, this always splits as an explicit direct sum of line bundles. Okay. So I'm going to let this theta be the possible summands of the toric-Frobenius, and then I want to go for all t, or actually I just need for t sufficiently large. Okay. So maybe a fact is that this is a finite set. And if you know this is the set of lattice points in the zonotope for. So there's some explicit polytope whose lattice points is this set in if you know some toric geometry. Okay. And so I want to describe this F. Well, I just wanted to recall F should be an object of this resolution. And right now, these guys are all in the associated line bundles to these guys would be, so here are the associated line bundles. O of D would be on X sigma. So I want to somehow get something um, in here, or actually these make sense on all these toric birational models. Okay. So what we do is we select, it turns out that screwed one thing up. There should be a minus. So maybe fact here is that theta is contained in minus the effective cone of X sigma. So there is a set of anti-effective divisors. And this is where the toric birational geometry comes into play, is that this is always the union from I equals 1 to t of the anti-Neff cones of the X sigma I. This should really say. So, each of the elements of theta lies in some Neff cone. So I can imagine that in some Neff cone, it turns out the picture kind of looks like this. So this might be the anti-effective cone, let's say, right? And this is like Neff X sigma 1, Neff X sigma 2, Neff X sigma 3, right? And you have some lattice points in here. This is your theta. Okay. And some of them could be on both, but the pullback will not change. So what we do is we take the pullback from their respective Neff cones and assemble it into this sum of line bundles on dx total. Okay, so that is the tilting object in the theorem. Does that make sense? Questions? Okay, so we take all sums of the toric Frobenius morphism, and then we pull back along the individual Neff cones, and if you're on this what's called a wall, it doesn't matter which pullback you get the same line bundle in dx total. Okay. So now that's basically the full description of the King's category theorem. So can I ask, am I supposed to go for 3 more minutes, or when am I supposed to stop?
15 minutes.
15 minutes? Okay. Okay. So okay. So next this is again anachronistic. So this happened before. I studied with Wang this algebra, which is the endomorphism algebra of these Frobenius line bundles. And we showed that the global dimension of this endomorphism algebra in this case, so this F is the F above. This is the tilting object for d Cox. Okay. So we showed that this had the global dimension of this algebra is the dimension of X sigma. And maybe if I went all the way back, I glossed over this earlier. So this is not the case. For King's tilting object. For FR. This was actually shown by myself and Ballard when I was a grad student with Gromov. Okay. Okay. So meaning sorry, what's not the case? What's not the case is that this equality. So actually the dimension is 3 if R is greater than equal. Okay. So this is not automatic, right? So what's the consequence here? Well, as we described, once you have a tilting object, this King's conjecture basically gives you that any coherent sheaf on X sigma has a resolution of the form has a resolution like this, where each of these is a sum of line bundles, and now we know specifically they're line bundles from this finite set up to twist. And where did I use this theorem on the global dimension? I used that when I take a when I do this algorithm and take a projective resolution, the length stops at exactly the dimension. So that was the that recovers the Burkesh-Ehrman-Smith conjecture again, proven by Hanlon, Hicks, Lazarus. Okay, so are there any questions? All right, so I'll do an example. So I'm going to return to the Herzebruck surface. Okay. So so this is a picture of the effective cone. This is the effective cone. And maybe I should draw the anti-effective cone. Not that it really matters, but I'm just using the typical basis. So this is the minus the effective cone of FR. Looks like this. So this is This here is minus the Neff cone of FR. And this one is actually minus the Neff cone of the weighted projective space P11R. Okay? And then there ends up being some number of guys here. So this number here, I should make this a little bigger. Yeah. Can I make it bigger? So maybe this is the picture when this is R equals 4. Okay. So notice that these guys here were actually the line bundles from King's this is King's set. Put it in another color. This is King's line bundles. And in this case, that's all you need. But we take more. We take these. And what happens? I'll give you some precise idea. So here I have the Hertzsprung surface, which is the same as its associated stack. But I have the variety P1, so I'll set P sub V 1 R. This is equals Praj in the Hartroni sense of KXYZ with weights 1 R of this graded ring. And here I have P1, what I'll call P11R. This is the stack. This is a variety. This is the weighted projective stack. Which can be thought of as maybe AN, A4, A3 minus 0 mod C star. It's quotient stack with weights 1 R. And it turns out in this case, this is the fiber product of this diagram. Or you can take this to be the fiber product. It's a fiber product is the root stack on FR for the minus R curve with multiplicity R. Okay. So take the rth root stack on the minus R curve here. That's what this thing ends up being. And so with R equals 4, so it turns out that you have this derived category of X tittle. This is strictly larger than this decox of FR. And this is the category generated just by maybe P star D of FR and Q star D of this weighted projective variety generated. So these actually overlap a lot, but this has, so that this thing has growth in D group rank. R plus 3. I think this one is rank R plus 4. And these each individually only have rank 4. Oh, sorry. Then D P11R. This is R plus 2. And the rank of this one is 4. Okay, so you can tell that these are all different, and that's where I'll stop.
Questions to the speaker?
Sorry, I'm trying to read.
I have a question, David.
Yes.
Actually, two questions. But so, what is the symplectic? I mean, what is the mirror of this this picture in particular of the Cox category and
Yeah.
the
Yeah.
show?
So I didn't say that, but that's a wonderful question. So maybe the FLTZ mirror tells you that if I take a torque variety X sigma, right, then I form, so this sigma is a fan in NR, and I can form this union sigma cross sigma perp over sigma and sigma. This is in the cotangent bundle. So this is in NR cross MR by M. So this is the cotangent bundle. This is the cotangent bundle to the mirror torus. Okay. And this thing is the Lagrangian skeleton. This is the mirror Lagrangian skeleton, according to FLTZ. So I'll define this thing as stack. And the FLTZ statement is that the derived category, so this is homological mirror symmetry in some sense, is that this is the Fukaya category of this cotangent bundle. It's like wrapped Fukaya category with this set of stops. Does that make sense so far? And now you're asking me what is the mirror picture? Well, I told you there was this dx sigma 1 through dx sigma t. And this is actually really how we got this idea, right? So these are all actually subcategories of the Fukai category of this cotangent bundle on a torus. If I take away the stops altogether, right? And in fact, I can add here one more thing. I can take the union of the stop data. And then so in fact, this is in some sense, the category generated by the Fukaya category of each of the mirrors, right? So through this homological mirror symmetry, this will correspond to this Cox category. And then the statement here, which goes back to bundle, basically, and was revisited recently by myself and Wang, is that this is the derived category. This has a natural tilting object. So in fact, well, let me say one more thing. So if I take this Fukaya category, this is by Nadler-Zaslow and Ganatra and Shenda. This is the microlocal sheaf category of something on a torus. It's just constructible sheaves on a torus with maybe some microlocal support like this. And I'll just use this same symbol with this microlocal support. And then this thing has a tilting object given by the functor, the object representing the stock functor. For all strata given by the stratification. Okay, so I'm saying this quickly, Pranav, but basically, when you take the union of all of these, you get more structure, and that structure is a stratification of the mirror torus that was originally identified by Bundle. That stratification of the mirror torus, in fact, in general, basically, if you have a nice stratification of a space, Wang and I proved that the stock functor gives a tilting object for sheaves, constructible sheaves on that space. So in this case, this is a nice stratification. The stock functor gives a tilting object, and what I described to you today was the mirror of that tilting object. Does that make sense?
Yeah. So so in principle, it's possible to give a completely A-side argument?
Yeah, and you can derive this from the A side.
I see.
And in fact, the paper with Sapronov used homological mirror symmetry to get all these resolutions.
Oh.
Yeah.
That's great. Thanks. That was great.
Yeah.
Other questions? So if there is none, then let's thank the speaker again.
Okay, thank you very much. I hope you have a wonderful
Thanks, David.
conference. Yeah.